Thank you. So, yes, good afternoon, good evening, and good morning, depending on which part of the world you are joining today. My name is Syeda S Razia. You have already heard that I'm a professor of Department of Chemical Engineering at Bangladesh University of Engineering and Technology, and I am involved with some of the activities of OPCW. I'll be introducing the topic chemical substitution today. So let's look at the chemical market, the global chemical market. World chemical sales that was valued almost 3.6 trillion in 2019. Basically, that was a 4.1% increase from the previous year. And evidently, the sale has declined a little bit during COVID period, but in 2021, industry is trying hard to recover from that decline. And if you look at the world map, you can see that China, NAFTA countries and EU countries are the main players in chemical market. But apart from that, we can see some of the Asian and Asia Pacific countries are also contributing significantly to chemical production or chemical sales. Now let us look into the number of or types of chemicals we are considering. A recent study in environmental science and technology says that they estimated almost 350,000 chemicals or chemical mixtures that have been registered for production and used globally. And their study is based on 22 chemical inventories from 19 different countries or regions. There may be some contradiction with the methodology, but we do have another source. If you look into the chemical abstract services, we can see that there are 235,000 chemical entities with chemical abstract service numbers. So that gives us some kind of idea that how many types of chemical we are actually considering when we are thinking of the global market. And of course, there is an additional 2,000 chemicals added every year in the market. Now let us let us discuss a little bit about the behavior of chemicals. We all know about this, but it's good to refresh our ideas and memories. Yes, chemicals are the solution to many of our problems, but definitely they are also cause of many hazards in our life. But when we talk about hazards, we need to understand that there is a concept of dose with it. I mean, many chemicals which we use as medicine, they are remedy for us in a smaller dose. But many of these chemicals, if you take it in a larger amount, that can be poison as well. So when we talk about hazardous chemicals, it would be nice to remember this fact that this hazard is also related to the dose or amount of chemicals we are using. And next, there is a concept of dose time response. It's not only dose, it's also the exposure time, which is important when you talk about hazardous chemicals. We all know Haber's law of toxic gaseous inhalation substance, or Drucker's law of cancer development. It says that exposure to a low level of a toxic chemical for a long period of time can cause the same results. For example, it can cause death as exposure to a high concentration for a short time. So when we talk about hazardous chemical and dose, we also need to remember that the exposure is also important. Even some dose of some hazardous chemical could be very low and not really that dangerous, but if we are exposed to it for a longer period of time, that can be really fatal as well, like a huge exposure of chemicals. So being said that, let us talk about what kind of exposure we face in our life. Chemicals reach us through products And everyday items such as home appliances, furnitures, cosmetics, cleaners, even food materials, they contain many known and unknown harmful chemicals. And of course, this is a chronic exposure as we use these chemicals every day and lifelong. So that means if these products have really very low level of any toxic chemical, still they are of concern because we are exposed to it for many, many hours and for lifelong time. Next, I'll discuss a defined type of exposure through chemical industry. In chemical industry, there is occupational hazards. Every year, more than 1 billion workers are exposed to hazardous substances. That includes pollutants, waste materials, dust, vapor, fumes in their working environment. And that also means they get fatal diseases and cancers and poisoning for chronic exposure. And sometimes they face fatal injuries because of fire or explosion, which we can say for acute exposure. And there is chemical disaster. For example, in 1976, a chemical plant in Sevaso released a dense cloud of dioxin that contaminated tens of square miles of land and more than 2,000 people it poisoned. So this kind of disaster, they can create acute exposure, but at the same time, they can have major impact on human life and on environment. Next, let us check what kind of chemicals are of our concern. Evidently, as we discussed and we know that chemicals of concern, they can be either health hazards, they can be either environmental hazards, or they can be physical hazards. And physical hazards is important in a way because, along with health hazards and environmental hazards, physical hazards are also important because they have the potential to cause major accident in industry and have major impact on community and in the business, chemical business. Interestingly enough, that there are chemicals, they can have only one hazard, but there are many chemicals that have more than one type of hazards. And there is another type of chemicals of concern, that is chemical security concern. Being part of OPCW, it is, it is befitting that I mention it, that there are the chemicals, those are security concern, are basically toxic and high volatile chemicals, but there are some chemicals which are not really toxic as such, but they can be used as precursors for chemical warfare agents. So OPCW really are focusing on those chemicals because they are used heavily in the industry. So these are of security concern. Next, let us go a little bit in detail about hazard classification. When we talk about health hazards, there are a number of categories in health hazard. We have acute toxicity, we have skin corrosion, skin irritation, eye effect, sensitization, we have carcinogenicity, mutagenicity, reproductive situation, even aspiration toxicity. But for environmental hazards, we have only two types of category, which is really focusing on aquatic life, aquatic toxicity. For physical hazards, there are a number of categories that ranges from explosives to flammable gases, liquids, oxidizing liquid, solid peroxide, and many other items. That's why physical hazards can be gas, liquid, or even solid, depending on the properties they're exhibiting. And this hazard classification I basically discuss is GHS, globally harmonized system. But there are other hazards which are not included in globally harmonized system or maybe any other system. For example, we all know about endocrine disrupting chemicals, EDC. And we know that these kind of chemicals can cause harm to human development, behavior, fertility, yet they are not codified under any kind of hazard category. And then there is ecotoxicology. I already mentioned that the GHS system is mainly focused on aquatic life, and the literature is heavily weighted toward aquatic system. But then ecotoxicology also means terrestrial organism, and impact of chemical hazards to terrestrial organism may be different than aquatic organism, and the interpretation could be different. So ecotoxicology need to include those items also. Being said that, let us discuss an example. We all know the latest trend of eye makeup, smokey eye. But then the history of smokey eye actually dates back more than 3,000 years BC. And I'll be a little bit talking about the Egyptian history. Men and women in ancient Egypt, they used Kohl, which was made from galena or lead, and they would wear it to complement their eyes, honoring their deities, or even maintaining hygiene. And we need to remember that this Kohl was worn by both poor and rich. And many belonging to lower classes, they had to substitute this lead or other minerals for fire suit because they were not able to afford galena or lead or other minerals. Now, if you now look at the modern times, there is still this fashion of Kohl, but in our time, we'll not find lead in the eyeliner called Kohl on the shelves of reputed brands like Sephora, MAC, or Revlon. Instead, they use amorphous carbon or charcoal, and they don't use lead. So that means even the rich people in modern time would not use lead because of their toxic properties. This is an interesting kind of study of hazardous chemical, and particularly the study of lead, which is interesting because lead is one of the best studied toxic substance. And as a result, we know more about the adverse health effects of lead than virtually any other chemical. And the health problems caused by lead have been well documented over a wide range of exposure on every continent. Still in 2019, lead exposure accounted for more than almost approximately 1 million deaths and 21.7 million years of healthy life lost. And this is one of the reasons it's interesting to note that although we know that lead is really toxic and it is well documented, but we are still fighting with it, and we could not get rid of lead from our day-to-day life. Because lead poisoning is not only an environmental disease, it is also a disease of lifestyle. It is included in many of our day-to-day life stuff, which we could not get rid of. And another important thing I would like to mention here, most of our hazardous chemicals in the market are not at all well studied like lead. So if this is the situation of lead, which is well studied and still we are fighting to get rid of that chemical from our life, what about the other hazardous chemicals, which are not even as well studied as lead? So of course, there is a problem of data and information for different hazardous chemicals. I would like to give you one example. Nike has developed Nike Consider design to measure the sustainability of its products. This required chemical data from suppliers, but then Nike encountered two types of challenges. First challenge, they found that the suppliers may not have or may be unwilling to share the information about the chemicals they use in the production process. And secondly, for many substances, they really surprisingly found out that hazard characteristics are still unknown. So that means there is really scarcity of information to develop, implement, or analyze new product. We need to understand that. And then another point is, even if some information is there, but it is not really accessible to everyone who wants to, work with less hazardous chemicals. So this is some of the challenges we are facing in our time. Now let us talk about chemical substitution. We have already known that hazardous chemicals are in our everyday use products and they can surely negatively impact our health and environment. But then chemical substitution has been prescribed by green chemistry, inherently safer design, and many rules and regular guidelines that it is an effective strategy to make products and process less hazardous. There are legislations that restrict the use of hazardous chemicals, and there is also a growing awareness among consumers about hazardous chemicals in products. But having said that, I would like to mention one thing, that for industrial sustainability, reduction of hazard from product is not enough. We also need to reduce hazard from the process to make it as a whole sustainable. Now let us look at some of the legislations we have for chemical substitution. EU REACH regulation and in US EPA have taken up substitution of chemicals harmful to human health and environment as one of their central elements of policies. And there is another policy like COMA, Control of Major Accident Hazards Regulation of HSC UK or Seveso directives of EU that recommend avoidance or reduction of major hazard chemicals at the source. And of course, there is OPCW, Organization for Prohibition of Chemical Weapons. It restricts and encourages substitution of some of the scheduled chemicals, which are precursors for chemical warfare agents. Now we learn that chemical substitution is really good for reduction of hazards, but there is regrettable substitution. We also need to learn that. So let us give some example of regrettable substitution. One important thing we need to remember that when we do chemical substitution, we really depend on our current state of knowledge, which is really evolving. So that means today's solutions may well be tomorrow's problem. A very good example is refrigerant. We know in early 19th century, Thomas Midgley, he created chlorofluorocarbon, a non-flammable and non-toxic refrigerant, which was a very good improvement from the toxic and flammable substances. But then in 1987, CFC was restricted because of its ozone layer depletion property. And then soon hydrofluorocarbon became most common alternative to CFC refrigerant, but then history repeated itself once again as the latest amendment to the Montreal Protocol require HFC refrigerants also to be phased out. Currently, what is happening? Currently, the researchers are working on new types of refrigerant, although some industry went back to some of those old flammable refrigerants. I would like to mention here one thing, that the webinar series we are having here by PSC for Speed, in webinar 3, they covered refrigerant design, selection, verification topic, and also they demonstrate tools with software Pro AFT. So if someone is interested, they can go back to the YouTube channel or the lectures, and you may find it very useful in terms of designing of new refrigerants. Now, when we talk about regrettable substitution, how to avoid that? So let us learn about informed chemical substitution and alternative assessment. What is informed chemical substitution? The goal of informed substitution, as defined by US EPA, to minimize the likelihood of unintended consequences, which can result from a precautionary shift away from a hazardous chemical without fully understanding the profile of potential alternatives, and to enable a course of action based on the best information that is available or can be estimated. So that means in summary, we can say that informed chemical substitution is basically a systematic approach to make best use of available information and prediction method for an efficient chemical substitution. So that's we will be talking about in our next slides. Sorry. So in informed substitution, there are a number of issues we need to address. The first point would be how to decide whether a chemical is hazardous enough for substitution, how to conduct comparative hazard assessment among alternatives, and what kind of knowledge representation will be most effective for navigation and systematic chemical substitutions. In my next slides, I'll be trying to shed a little bit of light on each of these topics. So which chemicals should be our first choice for substitution? Definitely the regulated chemicals. They are in urgent need of substitution. I will give you an example of regulated chemical PFAS, which has become very well known as forever chemicals. What is PFAS? PFAS is per and polyfluoroalkyl substances, and they have very strong bond between carbon and fluorine, and that's why they are heat, oil, and water resistant, and they're used in protective coatings, waterproof fabrics, and firefighting foam. And because their bond, carbon-fluorine bond, is so strong, they really do not degrade very fast. So they take longer time to degrade. They accumulate in human body and environment, and eventually they caused problems for human growth, children's growth, or even they actually cause cancer in our, in human body. So these are some of the reasons that people are becoming very concerned about these PFAS or forever chemicals. And there are regulations. EU POPs regulation is there to restrict these chemicals, and different states of US, they limit the amount of PFAS in drinking water. I will give you one specific example of PFAS in my next slide. You see, in textile finishing, we use two types of PFAS, perfluorooctane sulfonate and perfluorooctanoic acid. They are used as water and oil repellent for textile finishing of outwears. Now, if we want to look for alternatives for these two PFAS chemicals, we can check what is being used in the industry. One point we need to remember that only fluorinated compounds are really, they possess both water and oil repellent. So industry has already moved to short chain polyfluorinated compounds instead of PFAS. But then this fluorinated compound has the similar potential to cause harm to the environment and health, and they are actually included in rich regulated candidate list for high concern substances. So apart from this fluorinated compound, we do have other choices. Some are paraffin-based, silicone-based, polyurethane-based, even dendrimer-based. But the major problem with all these chemicals are they have lack of information about their composition. They could be potentially bioaccumulative. They could be even more toxic than some of the chemicals, than PFAS. And some of the chemicals are really, you could not validate suppliers' hazard data because they do not declare it because it is trade secret. So this is a major problem. So what is the major challenge here then? I would like to say the substances we want to replace, they have been well studied compared to the alternatives, which we have very little or no data. This is a real big challenge for an efficient chemical substitution. Now I would like to give you another case study of mosquito repellent. The chemicals involved in this repellent are really not regulated. They're non-regulated chemical. DEET is one of the active ingredient that can be found in mosquito repellent, but it is a bit skin and eye irritant and moderately harmful to aquatic life. So consumers may look for mosquito repellent, which is DEET-free. So if you want to look into some of the products, like some of the mosquito repellent, you can find some of the alternatives like picaridin, methyl nonylketone, ethyl propionate, or citronella oil. You can find this, and all of these chemicals, fortunately, are non-regulated. So there is no regulatory binding for this. But if you look into the properties of these chemicals, you'll see that each of these chemicals, they have different types of hazards, and some of which may not be directly comparable. So it is not always possible to make a right away decision which one is safer, which one is not safer, because some chemical are really a health hazard, some other chemical can be an environmental hazard. So how do you compare? So that is one of the challenges. And also, if you think about mosquito repellent, the atypical formulation of mosquito repellent includes other components than the active components, and hazardous properties of each ingredient within allowable range of the concentration need to be evaluated before we decide which mosquito repellent we are going to choose. So what is the requirement? A hazard scoring system. and threshold values for comparison of hazard potential of each ingredient of different formulation of a given product in order to make a decision on the safer product among some of the options. So this is one of the requirements we find out. Now I would like to draw your attention to product process connections. We need to have understanding of product and process when you want to have sustainable, process for the whole, alternative assessment or whole chemical substitution. For sustainability, manufacturing safer products is not enough. It is necessary to select the raw material from which they can be made and to design processes that can manufacture them in a sustainable manner. So we need to look into the raw materials, the processes, everything that is involved for manufacturing a safer product to make it sustainable. And a chemical used in a process or its operation, for example, as a solvent, diluent, lubricant, adsorbent, may need to be substituted for safety and sustainability. So we have products and we have chemicals in product, and then here is the process, and we have chemicals in the process. So chemical substitution is applicable for both products and processes. In this regard, I would like to share one of the case study for safer processes that was reported by Patel et al. In Journal of Loss Prevention. And this case study involves searching for alternatives for ethyl acetate, which is a solvent for extracting acetic acid from aqueous solution. Why we are looking for alternatives for ethyl acetate? Because it is very flammable and has the high potential to cause major accident. So it is inevidently, it is important to look for an alternative. So in this case study, what they did is that they first carry out a process simulation using the process condition and relevant parameters in a commercial simulator. And from this simulation, they figure out the requirement, the requirement of the process for the solvent. And then those requirements, they actually use in another software for alternative solvent assessment. Because when you want to find a appropriate solvent, you also need to understand in which system or in which process this solvent under which condition are going to be used. So these informations are used in alternative assessment for alternative solvent. And then these informations are again used in consequence modeling to check the potential for explosion for each of the alternatives. So in this case study, we see that there is process simulation, there is alternative solvent assessment, and there is consequence modeling for safety. So what happens after this? After this assessment, they found at least 3 alternative non-unknown, 2 non-unknown, and there is methyl 2-hexanone. Interestingly enough, 5 and 2 non-unknowns, they are very good. They are in terms of heat duty, heat energy requirement, and in terms of their safety. But unfortunately, the capacity of extraction is actually compromised if you use these chemicals. But then for methyl 2-hexanone, yes, it has very high separating capacity, but it has safety concern, and of course the energy requirement is high. So really, when we choose solvent which is appropriate for our system, we need to consider all of these parameters. So what are the conditions for choosing or selecting safer process chemicals? For safer process chemicals in process, we need to specify main functional role of this chemical in the process, along with the complete process description, including process operating parameters. These are the preconditions. Only alternative assessment will not help. Now let us look into the existing guidelines and tools for substitution. What we have right now, a number of international and regional authorities, state and provincial authorities, and research organizations, they are actively working in this field, and they have proposed number of tools, guidelines, even databases for chemical substitution. So we know that UNEP, they have persistent organic pollutants rules and regulation. REACH has authorization analysis of alternatives. Even OECD has its toolbox. US EPA has design for the environment alternatives assessment. And US also has interstate chemicals clearinghouse. And German Federal Environment Agency, they have proposed German guide on sustainable chemicals. And of course, California Safer Consumer Products Regulation is there at this provincial level. And then there are a number of research organizations which are really involved in chemical substitution. For example, TURI, Alternative Assessment, and LOL Center of Alternative Assessment Framework. Both of them belong to University of Massachusetts, Lowell. And then UCLA Multi-Criteria Decision Analysis, and then Swedish Center for Chemical Substitution, which is under the umbrella of RISE. So in this table, I'm quickly summarizing all the methods, tools, and database available currently. Detail of all the items in this table presented, you can find it in OECD Meta Review or the paper Jam et al. They published in 2019. And if someone is interested, you can always look into those and you could be benefited from the literature. Now, what are the gaps? If we look into all the existing frameworks and check very closely, the major gaps we can find that most of these frameworks, they provide guiding principles, but not specific protocols. And mostly they focused a handful of high-profile chemicals. They are limited by specific goals and applications. And they also focused individual substances rather than products. And of course, very few case studies dealing with safer processes. So these are the main gaps one can find in the existing frameworks. Now the question is, of course, there is no one-stop shopping option to identify safer chemicals. How do we proceed? In my next slides, I'll be giving a little bit hints or suggestion what could be our next step. First, we need to think seriously about data representation. We cannot just take the raw data and store it in the system. That is not going to help us. Data must be efficiently stored in an information system based on specific ontology. And the interconnectedness and interoperability of the ontology would address the challenges of accessing and retrieving data and navigation. For example, if we have a given chemical, this database should be able to generate all the property data for that chemical. Conversely, if we have some properties for some chemical, and if we supply these properties, the database should be able to give us a list of possible chemicals that has this kind of property. So it is important to have the data representation at that level to make the access and retrieve and data navigation flexible. And what about data integration? We know that ontologies would allow us to format unstructured, semi-structured, or structured data, and it will help us smoothen data integration, data mining, and data-driven analytics. So this is the first thing, data representation. So what we propose, since our ultimate goal is safer products, we suggest knowledge representation based on the products rather than individual chemical species for chemical substitution. Yes, definitely the database should have all properties for each and every chemical, but the representation should be product-based. For example, personal care, pharmaceuticals, cleaning product, clothing, food, fertilizer, insecticide, fuel, many types of product. And it should include all type of formulation and composition in the database. And then we should have physical chemical properties of each chemical and their functionality and how they behave when they are in a product. And then of course the hazardous effects of all chemicals in a formula. Being said that, what kind of framework we are suggesting? Yes, we are suggesting a framework where we will deal with product. A product of concern which can be a single chemical or a chemical mixture that will be analyzed first to find the candidates for chemical substitution for its ingredients. And next, we'll do the alternative assessment for all hazardous chemicals present in a product. And then finally, the safest among alternative product formulations will be accepted. That means we are not talking about only one single chemical. We are talking about the formula, the complete formula of a product. We are checking each and every ingredient of the product. We are checking their compatibility when we are doing the alternative assessment. And finally, we are accepting not a single chemical. We are accepting actually a particular formulation as a safer alternative. So this is what kind of framework we are expecting or we are suggesting. Now, what about framework for safer processes? Yes, we also have a proposal for framework for safer processes. For safer processes, we need to do the alternative assessment of process chemicals based on the functionality and its hazardous properties, but we also need to integrate with it process simulation and consequence modeling to get the best alternative for that particular process. Finally, the conclusion. In my conclusion, what I would like to say that there is a persisting need of establishing integrated and accessible database based on reliable experimental data and models for prediction and data fill-up. But apart from that, we would recommend product-oriented knowledge base and representation that would make the database more efficient. And for substitution of process chemicals, we'd recommend computer-aided tools for chemical substitution should be, just a second, excuse me. For substitution of process chemicals, we recommend computer-aided tools for chemical substitution that should be integrated with process simulation and consequence model to ensure safer process. And finally, transparency and disclosure of product components from manufacturers and traders is a precondition for successful chemical substitution. With that, I'm going to end my presentation. I'd like to acknowledge that part of the work I'm talking about is being carried out under the collaboration between PSC for Speed Company and CPI Safety Research Group of Chemical Engineering Department, BUET. With that, I'm ending my presentation. Thank you very much.
Thank you, Dr. Razia, for your very interesting presentation. So, audience, if you have any questions, please put your question in chat or show your hand so we can unmute you to ask your question. Thai office, can you check in the chat if there are any questions?
No, not yet.
Okay, while we are waiting, I may ask a question to Dr. Razia. So currently, what is the biggest problem in Bangladesh with respect to unwanted harmful chemicals?
Actually, we all know that textile industry is a huge industry in Bangladesh, and water pollution is a huge problem. So chemicals coming out from textile factories, they are the major concern for us. And if you could replace some of them in the upstream processes, it would be excellent for the environment here.
Okay, so I can ask this question to the participants also. Do you have similar experience with chemicals for textile or for other applications in your countries? Anybody would like to volunteer? There,
I saw Professor Zarqa from Egypt. He raised hand initially. Professor Mohammed Al Zarqa, did you have any comment at the beginning?
Can you unmute Professor Zarqa, please?
I don't know. I'm trying.
Yes,
He actually raised hand at the beginning, and I don't know.
Okay,
we have unmuted
And
him.
then-
already. Yes.
okay.
And
Any questions?
so I thought there would be lots of questions, and I was.
Yeah, looks like everybody is happy with the world and no chemicals involved. I can see that Dr. Michael Overcash is already joined us. So thank you for joining, and he will be talking next. Well, I will ask one more question then to see whether somebody else will after take over. So you mentioned that pollution is a big problem. Who is trying to solve this problem?
In our country, particularly when you talk about textile industries, we have three parties who are involved. The first one is definitely government, who's going to regulate. And then there is the industry themselves, they have associations. And there is the buyers. I mean, most of the, buyer, they are from European countries. I mean, Bangladesh export to EU or NAFTA countries. And then they have their, concern about pollution. And we do have in academia, we have lots of research going on, but whether it is going to be matters, we can produce tons of data, but then if the regulatory authority, they don't take up, they will not be able to, I mean, if they don't enforce it on the industry, we do not see it, happening in the industry, because any step for reducing environmental pollution, still they think it's an extra cost and it's a problem for the business. Sometimes when there is a pressure from buyers, they take up some of the, remedial measures. So yes, government, industry, and buyers, they have influence in reducing hazardous chemicals in our, in our what do you call it, water or in air. And there is also consumer awareness. They talk about it, but I don't see the consumers' awareness playing that of a very strong role in making decisions in our country particularly. And of course, a lot of research is going on how to reduce them. I just hope there will be a good coordination among the researchers and industry so that we can do something about it. We can perform better.
Okay, one more question then. If somebody wants to register a new product or a process, what are the steps they have to go through to confirm that they're not using any harmful chemical?
We have a number of act and regulations where they have to mention what kind of chemicals they are using. And also, there is a number of regulatory authorities who actually check whether you have hazardous chemicals. But my understanding is the resource they have to counter check all details of chemicals maybe not that strong, I guess. They have a number of lists under the act, and generally the regulatory authority go to the industry or look into the application and check against all those specific names. And if they see that those chemicals are not there, they are happy. But if there is new update in those chemicals, generally it takes longer time to get incorporated within the regulations. So if something is really regulated in Western country already, then may not be translated into the regulation we have here. So yes, there are a number of regulatory authorities, but it is possible to register new chemical, which is may be harmful, but is still not really regulated by the authorities.
Okay, so one last chance for anybody to ask a question to Dr. Razia. Okay, then thank you, Dr. Razia, for your very nice presentation. And then we move to the next speaker. And the next speaker is Dr. Michael Overcash. While Dr. Overcash, you share your screen and get ready, I will give the introduction, a brief introduction to you, and you can add more if you like. So, are you sharing your screen?
Yes, just I'm trying to get the PowerPoint located here.
Okay.